Good morning, students. Today we are going to discuss nuclei. So radius of the nucleus. So we are going to write the radius of the nucleus by using the formula R is equal to R naught times a to the power of 1 by 3. Where R naught is equal to 1.2 into 10 to the power of minus 15 meters. That is standard value, and a is equal to mass number. A is equal to mass number. So by using this formula, one can calculate the radius of any nucleus. Second one, volume of nucleus. How to calculate volume of nucleus? Generally, nucleus is the spherical in shape. That's why spherical in shape. That's why what is the volume? 4 by 3 pi r cube. R is the radius of the nucleus. But already we know that what is R? R naught a power 1 by 3. That's why volume is equal to 4 upon 3 pi times R means R naught a to the power of 1 by 3 whole cube. That is R cube. Now V is equal to 4 by 3 pi R naught a power 1 by 3 whole cube means R naught cube times a power 1 by 3 whole cube. So 3 cancel. So volume of any nucleus is equal to 4 by 3 pi R naught cube into A. So by using this formula, we can calculate volume of any nucleus. So 4 by 3 pi R naught cube is constant. Why? Because 4 by 3 constant, pi constant, R naught is also constant, 1.2 into 10 to the power of minus 15 meters. So volume depends upon the mass number. So if mass number increases, automatically volume also increases. Next, density of the nucleus. Density of the nucleus. So generally, density we are going to represent it with the symbol rho. So rho is the density. So density is equal to mass by volume. This is mass of the nucleus by volume of the nucleus. Suppose if I am going to consider mass of each nucleon is equal to A. Nucleon means the particle which is present inside the nucleus. Generally is called nucleon. Generally, protons present inside the nucleus, neutrons present inside the nucleus. The main mass components are protons and neutrons inside the nucleus. That is only responsible for the atom mass. So mass of the atom. So generally, mass of each nucleon, I am going to consider not A, M. Mass of the each nucleon, consider M. Mass of the each nucleon, consider M. So mass of each nucleon is M. Then what is the total mass of the nucleus? Mass of the nucleus. So mass of the each nucleon into total number of nucleons in the nucleus A. A is equal to what? Mass number. Mass number means total number of nucleons inside the nucleus. So mass of the each nucleon into total number of nucleons inside the nucleus. The multiplication will give the mass of the nucleus. Then rho is equal to what? Mass of the nucleus. Mass means here mass of the nucleus. That is how much? M into A. Volume of the nucleus. Already we proved, no? Volume of the nucleus 4 by 3 pi R naught cube into mass number. We derived, no, previously, that is only. So volume of the nucleus is 4 by 3 pi R naught cube into A. A cancel. Then rho is equal to what? M upon 4. This 3 goes to numerator. So 3M. 4 pi R naught cube. This is the density of the nucleus. Here 3 constant, mass of the each nucleon constant, 4 constant, pi constant, R naught constant. So everything is a constant. What is the mass of each nucleon? Nearly 1.67 into 10 to the power of minus 27 kgs. Nearly mass of each nucleon is 1.67 into 10 to the power of minus 27 kgs. Each mass of the nucleon nearly. So R naught value already we know that 1.2 into 10 to the power of minus 15 meters. So pi constant, 4 constant, 3 constant. Substitute all the values, you are going to get the density value nearly 2.3 into 10 to the power of 17 kg per meter cube. So density of the nucleus is same for all the nucleus. That is nearly 2.3 into 10 to the power of 17 kg per meter cube. So density of the nucleus for any atom is same. So constant. Note down, students. Next, mass defect. Mass defect. Suppose if I am going to consider Z is equal to what? Atomic number means number of protons. Number of protons. Z means number of protons. That is also known as atomic number, of course. Next one, A minus Z. A minus Z. That is number of neutrons. Number of neutrons. So number of neutrons. A minus Z. A minus Z. Number of neutrons. Then mass number. So A minus Z plus Z is equal to what? A minus Z plus Z. A minus Z is the number of neutrons inside the nucleus. Z is the number of protons inside the nucleus. Then A minus Z plus Z. A minus Z plus Z is the number of nucleons inside the nucleus. Total number of nucleons. So total number of nucleons inside the nucleus. So minus Z plus Z cancel. That is only we call it as A. So A is equal to what? Total number of nucleons. That is only we call it as mass number. What is the mass number? Total number of nucleons. Or we call it as number of nucleons inside the nucleus. Otherwise, proton mass plus total number of protons plus total number of neutrons. Total number of protons plus total number of neutrons. So remaining elementary particle mass I am going to neglect it. By neglecting elementary particle mass, I am going to consider number of nucleons. Any particle inside the nucleus, generally we call it as nucleus. Nucleons, so many elementary particles will be there. Their masses I am going to neglect it. Their mesons, muons, such a kind of elementary particle masses I am going to neglecting, and I am going to consider total number of nucleons. Generally protons and neutrons are responsible for the nucleus mass. That is only I consider here. That's why remember A minus Z is the number of neutrons. Then A is equal to, that means A minus Z plus Z. Z cancel, then A is the mass number. Mass number means what? Total number of nucleons. Proton number plus neutron number. That's all. Now, what is the mass defect? Let us see. If suppose I am going to consider Mn is the mass of neutron. Mp is the mass of proton. So if I am going to consider what is the number of protons? Z. One proton mass Mp. If I am going to get multiply these two, I am going to get what is the Zmp? Total mass of the protons. Total mass of the protons. Okay. A minus Z is the number of neutrons. Mn is the mass of each neutron. Then product is the total mass of the neutrons. Total mass of the neutrons. So Z protons, total mass Zmp. A minus Z neutrons, total mass A minus Z Mn. By combining, form a nucleus. By combining, form a nucleus. That nucleus mass I am going to consider Mn. Mn. Here what is Mn? Mass of the nucleus. I am going to consider Mn is equal to capital M. Capital Mn. Mass of the nucleus. Small mn, mass of the neutron. So this is considered capital Mn is the mass of the nucleus. Mass of the nucleus. So this is the total mass of the protons and the total mass of the neutrons before formation of the nucleus, and by combining these two these two types of particles, that is proton particles and neutron particles, by combining nucleus will form. That nucleus mass is Mn. So This is the total mass of the all particles before formation of the nucleus. This is the mass of the nucleus after formation by using these particles. Here what happened? Before formation of the nucleus, the total mass is greater. After formation of the nucleus, a little mass will be reduced. That mass helpful to bind all the nucleons together. So some mass will be converted as a energy. So that's why what happened? That energy is helpful to bind all the nucleons to form a nucleus. That reduced mass. That's why what happens? The mass of the nucleus will be less when compared to the mass of the all the constituent particles before formation of the nucleus. That reduced mass converted as energy. Of course, that's why what happens? Some mass will be reduced. That is known as mass defect. Then that mass defect we are going to represent it with symbol delta m. Then how to calculate delta m? Delta m is equal to difference between these two. That is ZMP plus A minus Z Mn. So from this I need to subtract mass of the nucleus. This difference will give mass defect. Mass defect. Okay. If suppose how to calculate mass defect in simple way. Remember delta m, if suppose in AMU, atomic mass unit. If delta m value, if you are going to substitute it in AMU, and you are going to get a binding energy, mass defect into 931.5 MeV. So delta m value calculate from this formula and substitute the delta m value in AMU. AMU is the mass unit, but that is not SI unit. It is the small unit of the mass, atomic mass unit. So substitute delta m in atomic mass unit and multiply it with 931.5. Then automatically binding energy you are going to get in million electron volts, MeV. Note down, students. The next one, law of radioactive decay. So what is the law of radioactive decay? Law of radioactive decay. Rate of decay is equal to minus lambda times number of nuclei. Rate of decay means derivative of n, which is equal to what? Minus lambda into number of nuclei. This is what? Radioactive decay. Here what happens? As time goes on, number of nuclei decreases. That is the negative symbol represents. As time, with respect to time, as time goes on, what happens? Decay is increases. So at the time what happens? Number of nuclei present, number of nuclei remaining will be decreases. As time goes on, number of nuclei remaining decreases. That is represented by negative symbol. So this is one of the formula, law of radioactive decay. And next one, n is equal to n naught e power minus lambda t. What is the meaning of this? So here n naught is the number of nuclei at t is equal to 0 seconds. At t is equal to 0 seconds means initial time. So initial number of mass, that is the n naught. N means what? Number of nuclei after time t. Here what is the time I am consider? After time t, what is the number of nuclei remaining? Why? Because some of the nuclei taking place decay, no? So after that, what is the number of nuclei present remaining? That is the n. Number of nuclei remaining at t is equal to t. That is after time t. Number of nuclei remaining. That is n is equal to n naught e power minus lambda t, where lambda is the decay constant. Lambda is equal to decay constant. Right, note down. Next one, half-life of a radioactive sample. How to calculate half-life? Half-life generally we are going to represent it with a T off. So we are going to calculate by using the formula log 2 base E by lambda, where lambda is equal to decay constant. Decay constant. And T off is equal to half-life. Half-life. And log 2 base E value constant. This is 0.693. Its value is standard and constant 0.693. So T off is equal to what? Log 2 base value 0.693 by lambda. Suppose in any problem lambda value is given, that is decay constant is given. He is asking half-life means use this formula T off is equal to 0.693 lambda. Suppose he is given half-life and we need to calculate decay constant means lambda is equal to from here 0.693 upon T off. So in the problem is given half-life and we need to calculate decay constant means these two are equivalent only. So decay constant is equal to 0.693 by half-life. Half-life value substituted here. In place of T off, substitute half-life value of a given radioactive sample. You are going to get decay constant. 0.693 by half-life will give the decay constant. Then what is the mean life? Mean life generally represented with a symbol tau. So tau is the mean life is equal to reciprocal of decay constant. Simply reciprocal of decay constant. That means tau is equal to what? Decay constant means 0.693 by T off. Otherwise reciprocal means 1 by lambda. Lambda means 0.693 by T off. Then 1 by lambda means reverse. T off by 0.693. By using this formula, if you know the half-life, substitute here, you are going to get the mean life of a given sample. But we know that 0.693 means what? Log 2 base E. That's why this is also write as tau is equal to simply T off upon what is 0.693? Log 2 base E. Log 2 base E. Sometimes out of 4 options is asking mean life and one of the option is given as T off by log 2 base E. Then we need to select that option. Note down students. Next one, after n half-lives, number of nuclei left, how to calculate? So where capital N is the number of nuclei left after n half-lives, or number of nuclei remaining after n half-lives, which is equal to n naught by 2 power n, where n naught is the number of nuclei at t is equal to 0. At t is equal to 0 means initially how many number of nuclei are present in the given sample. That is the n naught. Small n is equal to number of half-lives. Number of half-lives. So number of half-lives. So n naught by 2 power n will give the number of nuclei left after n half-lives. Here one half-life, T off means half-life, n is the number of half-lives. By multiplying these two, we are going to get a total time t. What is this time? Initially at t is equal to 0, we have n naught number of nuclei, and after time t is equal to t, we have n. From 0 to t time, n naught changes to n. Here n naught is greater, n is small. That means this is the number of nuclei remaining after time t. So how to calculate this time? Number of half-lives into half-life. By multiplying these two, we are going to get time. What is the meaning of this time? In this time, n naught changes to n. Here what happened? N is equal to n naught 2 power n, where small n is the number of half-lives. And what is t? After what time n naught changes to n? How to calculate? From this formula, calculate number of half-lives. So half-life multiplied with the number of half-lives, we are going to get the time. In this time, n0 changes to n. That's all. This is remember and calculate. And this is also can be written as n upon n0 transpose to left side. N upon n0 is equal to 1 by 2 power n. 1 by 2 power n. Of course, this is also can be written as n upon n0 is equal to 1 by 2 whole power n. So this is also one of the formula to calculate number of half-lives, where n0 is the total number of atoms in the given sample at t is equal to 0. Here n is the number of atoms remaining after time t. After time t, here number of half-lives. So n0 changes to n. N0 changes to n in time t. That time how to calculate? N into t half. Here n is the number of half-lives. Calculate from here, and half-life in the problem given me, substitute here. You are going to get the total time taken to change n0 to n. That's all. Note down, students. Next one, number of alpha particles and beta particles emitted. How to solve this problem in less time, let us see, in simplest way, and I am going to give the logic and the small tricks. X is equal to, we are going to consider number of alpha particle. What is the x here? Number of alpha particle. What is the y? Number of beta particles. What is the 4x here? Mass number difference. What is the 2x minus y? Atomic number difference. So 4x is the mass number difference, 2x minus y is the atomic number difference. This is the formula. Mass number difference formula 4x, atomic number difference formula 2x minus y. Just remember this trick, we are going to save the time. So here what happened? X is the number of alpha particle, y is the number of beta particle. So 4x means what? 4x means what? I am going to take one example problem and I am going to explain how to calculate alpha and beta particles. What is the problem? If uranium 92-238 decays to lead 82-206, find the number of alpha and beta particles emitted. So I need to calculate x and y. Why? Because x means number of alpha particle, y means number of beta particles. That's why I need to calculate x and y. But to calculate x and y, what is 4x? Mass number different. What is the 2x minus y? Atomic number difference in the given problem. What is 4x? Mass number different. What is the mass number here? 238. What is the mass number here? 206. What is the mass number difference? 238 minus 206. That is the mass number difference. Next, what is the 2x minus y? 2x minus y. Atomic number difference. In the given problem, what is the atomic number difference? This is the 92. This is the 82. Then what is the atomic number difference? That is the 2x minus y. Means atomic number difference. 92 minus 82. Right. What is the 4x value from here? 4x is equal to 238 minus 206. Just to subtract it, you are going to get nearly 32. 32. 238 minus 206. How much? 32. 92 minus 82. How much? 92 minus 82. That is 2x minus y. 2x minus y. How much? 92 minus 82? 10. Right. Here 4 get cancelled here 8 times. Then what is our x? 8. What is our x? 8. What is x? Number of alpha particles. So 8 alpha particles emitted. How many number of beta particles? Substitute x here. 2 8 jars 16. Why? Because x is 8. 2 8 jars 16 minus y is equal to 10. From here what is y? From here what is y? Y transpose to right side as a plus y. 10 transpose to left side as a minus 10. 16 minus 10. 16 minus 10. 6 is equal to y. Then y value how much? 6. X value 8. What is x? Number of alpha particle. What is y? Number of beta particle. So in this problem, 8 alpha particle, 6 beta particle. That's all. This is the simplest way to solve the problem. The thing we need to remember, 4x is the mass number difference, 2x minus y is the atomic number difference. So mass number difference is equal to 4x and substitute, calculate the x. Atomic number difference is 2x minus y. Take the atomic number difference and x value substitute in here and calculate y. You are going to get the number of beta particles. That's all. This is the simple logic to calculate number of alpha particles and number of beta particles. Note down, students. Next one, parallel radioactive disintegration. So, consider radioactive substance. Simultaneously, it emit that is parallel emission. It taking place parallel emission alpha and beta. On radioactive substance, parallelly disintegrate alpha and beta. So disintegration of alpha, disintegration of beta. So radioactive substance parallelly emitted alpha and beta particles. Right. T1 is the half-life, lambda 1 is the decay constant for alpha emission. T2 and lambda 2 are half-life and decay constant for beta emission. Total decay constant is lambda I am going to consider. Then how to calculate lambda? Total decay constant. Lambda 1 decay constant for alpha emission plus decay constant for beta emission lambda 2. But lambda is nothing but already we know that 0.693 by lambda decay constant is equal to T off we consider. That is called half-life. Here T1 is the half-life for alpha emission, T2 is the half-life for beta emission. Then how the formula will change? T is equal to, that is T1 is equal to half-life of alpha emission. Time period of half-life of alpha emission. So T1 is the half-life for alpha emission. That's why 0.693 by lambda 1. Then what is T2? Half-life for beta emission. That is nothing but 0.693 by its decay constant lambda 2. Lambda 2. Now lambda means simply 0.693 by T. What is T? Effective half-life or average half-life we call it as. Is equal to what is lambda 1 from here? T1 is equal to 0.693 by lambda 1. From here lambda 1 is equal to 0.693 by T1. That is 0.693 by T1 plus lambda 2. Here T1 is equal to 0.693 by lambda 1. Here lambda 1 is equal to 0.693 by T1. That is I wrote here. The next one is T2 is equal to 0.693 by lambda 2. From here lambda 2 means 0.693 by T2. 0.693 by T2. Now take the 0.693 common from the right hand side and cancel out both sides. And what remains? 1 by T is equal to 1 by T1 plus 1 by T2. By simplifying this, we are going to get T is equal to what? Product of T1 and T2 by addition of T1 and T2. So this is the required formula to calculate average life or effective life, where T is called average life or effective life. So by using this formula, we can calculate average life. T is equal to T1, T2 by T1 plus T2, where T1 is the half-life for alpha emission, T2 is the half-life for beta emission. If you know these two, then we are going to calculate effective half-life or average half-life by using this formula. This is called average half-life. Average, T is the average half-life or effective half-life. T is equal to average half-life. This is the half-life. Average half-life or effective half-life. How to calculate? T1, T2 by T1 plus T2, where T1 is the half-life for alpha emission, T2 is the half-life for beta emission. T1, T2 given in the problem, we can calculate effective half-life or average half-life by using the formula T is equal to T1, T2 by T1 plus T2. That's all. Thank you, students.